Welcome, everyone. Today, we're very happy to have one of our MSRI postdocs, Qing Zhang, who's going to be telling us about modular categories with transitive Galois actions.
Thanks, Noah. Hi, my name is Qing Zhang, and I recently graduated from Texas A&M, and my advisor was Eric Raw. Right now, I'm a postdoc at MSRI in the quantum symmetry program. In the future, I will go to Purdue for a postdoc working with Sean Sui. And today I'm going to talk about modular categories with transitive Galois action. This is a joint work with Richard Ying, who is my mentor here at MSRI, and Yilong Wang, who is also a postdoc with Richard at LSU. In this talk, we consider modular categories over complex numbers, which are ribbon fusion categories with non-degenerate grading. And we consider modular categories with modular data S and T, where the S matrix is obtained by evaluating the trace of the double braiding, and the T is a diagonal matrix with the twist of simple objects on its diagonal entries. The entries of S and T have certain restrictions. For example, by Weisser's theorem, the T always has finite order. So the twist of the simple objects are always root of unity. And the entries of T lies in a cyclotomic field. It is also interesting to consider the field extension of Q adjoining the entries of S. In 1991, De Boer and Hurry, in the study of rational conformal field theory, they show that the Galois group of the field extension of Q adjoining the entries of S is always abelian. By Kronecker-Weber theorem, which states any finite abelian extension of Q lives inside of cyclotomic field. So just like the entries of T, the entries of S also live inside of a cyclotomic field. In 2010, Ying and Schoenberg showed that the entries of S sit inside of the N cyclotomic field, while N is the order of the T matrix. This fact is useful in the classification of modular tensor categories. For example, Galois action was used in the classification of rank 4, which was done by Rowell, Stone, and Wang. And it was also used in the classification of rank 5, done by Bluyard, Ying, Rowell, and Wang. So our project was motivated by this process of classification. Roughly speaking, to classify modular tensor categories at certain rank, we first consider all the abelian subgroup of the symmetric group SR, where R is the rank of the category. And then for each case of the Galois group, we try to figure out the corresponding modular tensor categories. So we are motivated by this process of classification, and we ask the following question: can we classify modular tensor categories by the number of Galois orbits? As a first step towards answering this question, we consider an extreme case, which is what are all modular tensor categories when the Galois action has only one Galois orbit, which means the Galois action is transitive. So this is contained in the title of today's talk. Before talking about such modular tensor categories, I want to first introduce some known results from the representation of SL2Z of a modular tensor category. From there, we will see the S and T matrix sit inside of certain cyclotomic field. And after that, I will talk about how the Galois group acts on the set of simple objects. So let's begin. For any modular tensor category, it gives a SL2Z representation. So we consider a modular tensor category with a normalized modular data S and T. The factor that it gives us SL2Z representation is from that S and T satisfy certain restrictions. For example, S to the power of 4 equals to the global dimension square times identity matrix, and S times T cubed equals to a number multiply S squared. To be more specific, this number is defined by a summation of sigma and the dimension of each square of the dimension of each simple object, which we call them Gauss sum. The SL2Z, the group of SL2Z has two generators, where S is off-diagonal matrix and T is up triangular. S and T satisfies the compare those two relations, and if we map the generator of S to the modular S and T to the modular data, this gives us a projective representation of SL2Z. This projective representation can be lifted to linear representation. In this talk, we will focus on the following linear representation, the following lifting, where we define this little s to be a normalization of the original s by square root of the global dimension, and then we normalize t by gamma, and gamma is any third root of the multiplicative central charge. This way, we obtain a linear representation rho of SL2Z. And it was proved by Dong, Lin, and Yin. If the order of the normalized T is n, then the representation has kernel or congruent subgroup of level n. As a consequence, this representation factors through a finite group, SL2Z mod n. Moreover, the image of this linear representation sits inside a cyclotomic field, nth cyclotomic field, where n is the order of the normalized T. So in particular, the entries of S lives in this cyclotomic field, and it is an abelian extension. For any modular tensor category C, we denote the Galois group of this extension by GC. And using the Verlinder formula for modular category, every simple object Y gives rise to a character of the fusion ring, while the character chi Y sends simple object X to Sxy over S1y. And chi Y in for any simple object Y, this forms the set of irreducible characters of the fusion ring. Therefore, if we take any element in the Galois group and we act on Sxy divided by X1y, and there's a unique permutation such that sigma acting on this gives you a sigma hat permuting the simple object y. This is how the Galois group acting on the entries of F. So we have enough background to talk about transitive modular categories with transitive Galois action. Before we jump to the next slide, let's recall here, we call this Galois group GC. And we define transitive modular category as follows. A modular category C is called transitive if GC acts transitively on the set of simple objects. It turns out transitivity is a very interesting property. And in the following of this talk, I will tell you what are the interesting results we found as we go along. Our first major observation is that transitivity implies irreducibility. To be more specific, if a modular category is transitive, then the modular representation is irreducible. Why we think this result is important? As we mentioned earlier, the modular representation rho facts through a finite group SL2Z mod n. Using Chinese remainder theorem, we can reduce the irreducible representation of SL2Z mod n to the case when n is a prime power. And the irreducible representation of SL2Z mod prime power are classified in the literature. So by showing that the representation is irreducible, we reduce this question to some known result. That's why we think this is the first remark of being transitive. So let's take a look at our first example, which is a Fibonacci category. It has two simple objects, 1 and tau. The non-trivial fusion rho is given by tau tensor tau equals 1 plus tau. So we can observe here that the non-trivial object tau tensor generates the whole modular category. And the quantum dimensions are given by 1 and the Gordon ratio. And the S matrix is given as follows. And notice that Q adjoining the entries of F is the same as Q adjoining square root of 5. To figure out what is the Galois group of this category, we divide the second row by the dimension d tau. And we notice that the Galois group is actually generated by a Galois element which maps square root of 5 to negative square root of 5. So the Galois group is isomorphic to Z2. And notice here, the order of the Galois group is exactly the same as the number of simple objects. In general, this is true for every transitive modular category. And we have the following result, which transitivity implies fixed point free. And we have this proposition. If a modular category is transitive, then the order of the Galois group is the same as the rank of the category. This result comes from the fact that any transitive abelian action is also fixed point free. In particular, the order of the Galois group is the same as the order of the number of simple objects. So GC acts freely and transitively on this set of simple objects. This proposition allows us to uniquely identify the elements of GC and the simple object of the modular category. And it is also useful as a criterion to check if a category is transitive or not. Let's look at an example. We know that the Fibonacci category is transitive. So we want to take the delinked tensor product of this and to check if it is still transitive. The S matrix up to permutation of row and columns is equal to the canonical product of these two S matrices. So we can see that Q adjoining the entries of this new category is the same as the old one, which is still Q adjoining square root of 5. So GC is still isomorphic to Z2. However, by taking the delinked tensor product, the number of irreducibles increased by 2. So this is now equal. By the proposition, we know this category is not transitive. So one question to ask here is when the delinked tensor product is transitive. And we answer this question by this corollary. Let C and D to be modular categories, then the delinked tensor product of C and D is transitive if and only if both of them are transitive. And the field extensions of Q adjoining dimension of C and Q adjoining dimension of D is trivial. Okay, so using this result, we can check when the delinked tensor product of two modular category is transitive. So let's take a look at our second example, which is PSU2 level 5. It is a subcategory of SU2 level 5. It has 3 simple objects, 1, alpha, and lambda. The non-trivial fusion rows are given as follows. Notice here that either alpha or beta can tensor generate the whole category. And the S matrix can be given as follows. In particular, the S matrix can be written in terms of the dimension of the object alpha. And by some computation, we can show that PSU2 level 5 is transitive. And if we take the delinked tensor product of Fibonacci and this modular category, it is still transitive, since the Q adjoined the dimension of Fibonacci is the same as Q adjoined square root of 5, and Q adjoined the dimension of PSU2 level 5 is still the same as Q adjoined the alpha, which the intersection is trivial. And in fact, Fibonacci is also one of this kind. It is actually PSU2 level 3. So it is worth to take a look at the general case, which is PSU2 level P-2, which is a subcategory of a modular category SU2 level P-2. So let's first look at the big modular category, which is from the representation of UQSL2, where Q is a root of 2P, while P is a prime. It has P-1 simple objects, and we label them starting from 0 to P-2. And X1 is a generating object. And here is an example of tensoring with X. However, this category is not transitive. To say why it is not transitive, we note here that the last simple object tensored itself is the unit object. And we proved that transitivity implies that there's no non-trivial invertible object in the modular tensor category. Therefore, SU2 level P-2 cannot be transitive. So now we're thinking about if we throw away this non-trivial invertible part and we get a subcategory which we call PSU2 level P-2. And we label the simple objects are just those from the SU2 level P-2 with even label. And here is an example of fusion rod tensoring with X2. In fact, in this category, every non-trivial simple object generates the whole modular category. And the S matrix can be given as quantum integers indexed by I and J, and the T matrix can be given by the root Q. And in general, if we take a Galois conjugation of this modular category, we can get other ones. And here we call them Galois conjugates of PSU2 level P-2. It turns out this modular category in general is transitive. To see why it is transitive, we can first look at Sij over S0j, which is this quantum integer. And notice here, we change the root to q to the power of 2j plus 1. To check it is transitive, it suffices to check j lies in the orbit of 0, using the fact that p is a prime number and 2j plus 1 is relatively prime to 2p. We know there's always an element in the Galois group that maps 0 to j. So j lies inside of the orbit of 0 for any j. Therefore, this category is transitive. Moreover, this category is also a prime modular category. We call a modular category is a prime if every of its modular subcategory is equivalent to itself or the VEC. And recall we mentioned earlier, any non-trivial or simple object in this category generates the whole category. Therefore, PSU2 level P-2 can never be is a prime category. So now we give an example of a transitive prime category. In fact, up to Galois conjugation, these are all the prime transitive modular categories. And we have the following theorem. We consider a non-trivial modular category. Then C is prime and transitive if and only if the order of the T matrix is a prime P greater than 3, and C is equivalent to Galois conjugation of PSU2 level P-2 as modular category. So this is a description of prime transitive modular category. So why we are interested in considering prime ones first? This is because of the factorization theorem of modular categories. Milger's theorem states that every modular category is equivalent to a finite Deligne tensor product of prime ones. However, this this prime factorization is not unique, and there's one case when this is unique, which was given by Davidoff, Milger, Nichters, and Ostrich. So when the pointed part of this modular category is trivial, then the prime factorization is unique up to permutation of factors. So recall that, as we mentioned earlier, transitivity implies no non-trivial invertible object, and C-pointed is a maximal subcategory generated by non-trivial pointed object. So for transitive modular categories, we have unique factorization. To be more specific, we have the following theorem. we consider C to be a transitive modular category, then every fusion subcategory is a transitive modular subcategory, and the prime factorization is unique up to permutation of factors. So at this point, let's review some of the interesting results coming from transitivity. Our first building block is that transitivity implies that the SL2Z representation is irreducible. So we can reduce this problem to some known results. And we also find that transitivity implies that the Galois action also fixes no points. So we can uniquely identify the Galois group elements with a set of simple objects. And we also find that transitivity implies that there's no non-trivial invertible object. As a consequence, we have unique factorization of transitive modular categories. As we mentioned earlier, we have a classification of prime transitive modular categories. So we have our final result for transitive modular categories. If C is a non-trivial modular category, then C is transitive if and only if C is equivalent to a Deligne product of prime transitive modular categories. And the T matrices all have distinct orders. In particular, the order of T is a square-free odd integer greater than 3. Combine this theorem with the previous result, we know that all transitive modular categories can be given by PSU2 level P-2 up to Galois conjugation. This is all I want to talk about today. Thank you.
All right, any questions?
Yeah, I have a simple question. So I'm a bit unfamiliar with the Galois conjugates of these categories. So does one understand kind of very explicitly what all the Galois conjugates of this PSU2 level P-2 are?
Sorry.
So you have
Galois conjugates of this. So
yeah, because you're saying all the prime ones are Galois conjugates of this one particular category. So I'm just wondering how explicitly that actually.
You obtain them by change the root here, and they are all inequivalent as modular categories.
So the level one is the one where you choose the root of unity to be the one that's e to the 2 pi I over whatever that number is, right? And then, but you could choose any other root of unity that was the same kind of root of unity.
Okay, so they're basically
this is like this is a Q, and you change it by Galois conjugate. That's what I mean.
So they look exactly the same, basically, all the categorically.
They are not the same as modular categories. The fusion roles are the same.
Yeah.
But yeah.
Okay, thanks.
No problem.
I mean, in a sense, Galois conjugate, like, that's the whole point of Galois conjugates is algebraically, until you start asking questions about like embeddings into R or something, right? Like,
what exactly is this number?
Yeah. There's some questions in chat from Pablo, which I am gonna read out, and one from Andrew, which I will get to after that. So Pablo asks, I have a few questions. On slide 5, for the Galois action, given any sigma, is sigma hat easy to find?
For any modular tensor category,
Yeah, so which is the sigma? Is sigma this is supposed to be on slide 5.
This?
Oh, no. Surely this is the lifting. Yeah. It's this,
It's also sometimes by abuse of notation, we use this sigma hat the same as sigma, but usually how to find them? We first choose a Galois element from the cyclotomic field and try to see if there's some corresponding ones that maps this to this. I don't know if that answers the question.
but like, how much do you need to know about like, if I just tell you the S matrix, is it easy to figure out what sigma hat? So
Oh,
let's see. So how to?
I think first we divide the S matrix by the first row, and we have a list of algebraic numbers, and we try to see how you permute them. Usually, I will first what I will do is I first compute the eigenvalues of the fusion matrix, and then I put this I can recover the characteristic polynomial of the fusion matrix, and then I ask a computer to see what is a Galois group of this polynomial, and then I can guess. But usually you can, for large rank, it takes time to decide. But there's a hint that your Galois elements comes from the cyclotomic, the Galois extension of the cyclotomic field. So there are some routes you can choose to permute.
Great. So Pablo's next question is about slide 11. Could you jump to slide 11? Pablo 11. Says, thank you for the answer to that question. He seems happy with it.
11. Okay.
There we are. So the first condition seems reasonable. Pablo, is the first, what do you mean by the first condition? Slide 10, go back one slide.
Okay.
Great. So in the theorem, so the first condition, you mean the sorry, slide 9, go back. Great, I see. Okay, so C tensor D is transitive if and only if both C and D are transitive. Okay, great. The first condition seems reasonable. How is the second condition contributing to the transitivity of the Deligne tensor product? So could you just say a few words about what condition 2 has to do with this theorem?
Well, being transitive is a very strong condition. So for example, Fibonacci tensor Fibonacci, it doesn't satisfy this property. That means possibly you have one Galois element from one part of a Deligne tensor product that will affect the other one. That's intuitively that is why we have this second condition. Yeah.
I see. So it's like if the Galois group is gonna act transitively, it can't act this. Yeah, you can't have had the same action. Yeah.
Yes, it comes from it actually comes from that the Galois group, order of the Galois group is the same as the number of simple objects. It's very strong condition, and you cannot add like some free things into it. So yeah.
Okay, and then one last question from Pablo. He said this explanation was great for him. How about on slide 14?
14.
Right. So here you assume that P is not 2. Do you know anything about what happens when P is 2?
P is 2, then this is the level 0.
Yeah, but yeah.
I think it corresponds to trivial ones. If P is 2, then from the representation, we know it corresponds to trivial ones, which we don't care too much about it because you only have one simple object. So for sure, it is transitive.
I think it's not assumed here that P is not equal to 2. It's conclusion of this
the
theorem.
Conclusion. Got it. Okay, great. Yes. So great. So this says there are none with P is 2. I mean, the trivial one doesn't actually have P is 2 because the order is 1. Great. Okay. That's all of Pablo's questions. So Andrew wants. I see. Andrew was actually responding to Pablo's question. Sorry, I misunderstood that. Julia wants to know, you listed a lot of things that are applied by transitivity. Is any of this implication an if and only if? Do you have any kind of sufficient conditions for transitivity?
That is a good question. I think I'm not sure, but I suspect the second one might be if and only if, but probably we can. I don't know. Last time Elon said that, yeah, we have some disagreement, but no, I don't have any. I don't have any idea if any of them is the inverse is correct.
Any other questions?
So what might be next step? Study categories with 2 orbits on the Galois action? I mean.
Yeah, that is a good question. I have no idea. I think we have some candidates that the orbit is 2, but it could be hard because for this case, it's very strong because the modular category is self-dual, and I think for having 2 orbits, it could be non-self-dual, and it could be some. I have no idea. But if the other extreme case is the Galois action fixes everything, so this gives you so that means the first row of the S matrix is rational, and since the quantum dimension are always algebraic integers, so that means the dimension of simple objects are integral. So this reduces to the case of classification of integral modular categories.
Thank you.
No problem.
All right. Any other questions? Well, I've pasted the tea room link in the chat in case anyone wants to go there, and let's all thank Qing again.
Thank you.